All right, well, if you're watching this video, it means you're enrolled in Chemistry 220A, the graduate statistical mechanics and thermodynamics course in the chemistry department. So my name is David Limmer. I'll be your instructor. Um, it's going to be an interesting semester. It's the first full semester will be all virtual in light of COVID. But I think this is going to be a good semester. I'm looking forward to meeting you all during the live sessions and office hours. Because it's virtual, I hope that you'll take lofty advantage of reaching out to me directly on email. But to go and start this first lecture, I wanted to begin by trying an experiment. So I'm a theorist. I'm not very good at this, so we'll see how it goes. What I'd like you all to do in the comfort of your own homes, if you have the wherewithal and the equipment, is to grab a glass of water. I've got one here. And find some liquid that has some bright color. I happen to have some red liquid here. Now you probably don't have a dropper, but any old spoon will do. What I'm going to do for you here is I'm going to very carefully put this liquid in this wine glass. Now this is pretty close to density match, so the liquid in principle wouldn't sink, but I'm going to go ahead and put it at the bottom of the glass here. Very carefully. Like so. So now you see that it's sitting at the bottom of the glass. Now this liquid is just tinted water. So that means it should be miscible in the wine glass. So the experiment we're doing right now is one in diffusion. So that is to say that the equilibrium state of this system, colored water in regular old tap water, should be well mixed. We should eventually find that this little red blob equally distributes itself through the glass. So we obviously don't see that happening right now. So I'm going to set it aside, give the lecture, and we'll come back to this at the end of the lecture. All right. Putting that aside, the rest of this lecture, as all the other lectures will be done using an app where I can write out the notes. So I'm going to switch that and go ahead and begin kind of the formal part of the lecture. So stay tuned for updates with regard to our little ink drop. All right, so as I said, this is the first lecture in Chemistry 220A, which is a course on thermodynamics and statistical mechanics. So this is a course which I'm not going to presume that you have any background in statistical mechanics. I will assume only that you have some basic working knowledge of thermodynamics, that you've heard of, for example, the first and second laws before. What we're going to do throughout this course is really try to build up from the ground level, from microscopic principles, the whole topic of thermodynamics and see how it can be applied in the context of chemistry. Before we get into all of that, today I want to start simple. I want to think back to that glass of water that I showed you right at the top of the lecture. So a glass of water, if I was going to draw it out, look something like this. There's my glass. Let's fill it with water. So here water will be slightly tinted blue. Artistic sensibilities. Now, if you had that glass of water out in front of you that we filled up just a moment ago, what would you see? So I'm staring at that wine glass filled with water. It's got a little ink drop at the bottom. I could stare at this all day and not really see anything interesting. It's placid. Its shape is not changing. It's not undergoing any significant motion that I can tell by eye. And yet, you all, as chemists, know something about what that liquid is made up of. If we were able to see with X-ray vision, on the finest scales, angstroms or so, we could, you all know, observe that making up that glass of water are molecules. In this case, if your tap water is like my tap water, made out of largely H2O molecules. It's filled with tons of them. So many, it's almost uncountable. You know, that little glass of water that I filled up likely has about 10 to the 24 molecules in it. Overexcited. Not only is it filled with molecules, is it actually granular on the finest scale, something that we can't perceive by eye, but those molecules are in constant motion. They are continuously vibrating, rotating, tumbling over each other in what is a fairly chaotic behavior. And yet when we look at that glass of water, we don't see any of that excitement. We just see a boring old bulk liquid. So while we can't directly observe that motion, its implications are everywhere. In fact, its implications are in that experiment we're trying to do. For example, if we considered that ink drop, here's a little schematic of what we did. If we put that ink in the glass of water, our colored liquid, that colored liquid is made out of some number of dye molecules that happen to absorb light in the right way, such that they look, in my case, red. Those molecules, just like the water that surround them, are also in constant motion. The water will bump into those molecules, causing them to move. And the first implication of all that motion is that if we were to wait over some time, we know what's going to happen. We should expect that if that ink is miscible, and it's a water-based ink in our case, that if we wait a long enough amount of time, that ink should spread through the glass. Now, I've given you some heuristics that explains or reminds you that both the ink and the liquid that surround it are made out of molecules and thus are in motion, but what is the impetus for that ink to spread out through the glass? Why does this actually happen as we go forward in time? Another way to ask that is, does the reverse ever happen? Should we ever expect to see an initially well-dispersed ink in liquid water spontaneously coalesce back into an ink drop? And if not, why not? What if we were able to actually follow an individual dye molecule? Would this apparent irreversibility, this apparent directionality to time, be as evident? So we can't, unfortunately, see an individual dye molecules, but I know how their motion proceeds, at least a reasonable approximation to its motion. So as a theorist and a computational person, we could try to simulate it and see what would happen in order to ask or address this question of what would happen if we were able to probe the system on its smallest length scales. So let's actually consider that. Let's think of some simulations of this sort of behavior. So to start, here's our canonical glass of water and a molecular dynamics rendering of the constituent molecules. Here, red denotes an oxygen, white its associated hydrogens. The dashed lines are the hydrogen bonds that water makes with its neighbors. And if I was going to play a characteristic molecular dynamics trajectory or rendering thereof, this is what you'd see. Indeed, those waters constantly break and form hydrogen bonds. They rotate. Here, the vibrations are happening fast enough that I've just held them fixed. Otherwise, they would blur your eyes. Watching that motion, you get a real sense for just how chaotic that fluid really is, that somehow lying underneath this boring old glass of water is some really complicated behavior. So what would happen then if we put that dye and study how individual dye molecules might move around? So here's a different resolution simulation of that canonical dye drop, here shown, get my little pointer out, shown at the top of my little cartoon of a water glass. This is a simulation that essentially acknowledges that motion of a dye molecule in a fluid is random. So I can simulate it as a random walk. Molecules are going to be equally likely to move to the left and to the right, up or down, provided they stay in the glass. With those simple rules, if we started a bunch of dye molecules up at the top of the glass and played it forward in time, so ran this simulation. Indeed, the simulation corresponds to what you'd expect reality to do. The initially concentrated dye drop begins to spread through the glass. If we had a lot of patience, we're willing to wait enough time, we would see that it would uniformly distribute itself through the glass. Now, here is an example of a simulation where there are 50,000 odd dye molecules, so you can't make an individual one out so well. Let's scale that number down by a factor of 50. So here I've got a droplet corresponding with about 1,000 dye molecules, where we can start to see their granularity a little bit. And if I play that simulation forward, the same basic behavior occurs again. The initially concentrated drop expands, fills the glass. This is no different than what you'd expect a bunch of air molecules initially put up into the corner of your room to do. They would, that dense packing of air would expand rapidly to fill the room. It's the definition of a fluid. That apparent directionality, starting somewhere and ending somewhere else and not reversing itself, is though kind of peculiar. I told you the rules of this simulation are such that a molecule is equally likely to go up or down, left or right. So why does it fill the glass? let's scale this down by another factor of 10. Whoop. So here, now I only have 10 molecules in my glass. Now you can see them all. Now I want you to pick one of them and follow it in time. So maybe you picked one that is now pretty far away from where it started, but maybe you picked one, say this one, that has actually returned to where it started. So it actually did reverse itself. That individual molecule, now I'm following with the cursor, has apparently reversed what seems like a very irreversible process. You never, in your common experience, see a dye spontaneously go from well mixed in your solution to concentrated back into a single spot. And yet that molecule does, an individual one does. Am I playing a trick? So I can try to convince you that, you know, this isn't a game, I'm not pulling your leg. Here's back to 1,000 dye molecules where I've just highlighted 5 of them. If I follow one of those highlighted ones, indeed, maybe it takes excursions away from that initial concentrated point, but if you follow it long enough, it does return. So what's going on here? If we are able actually to follow an individual dye molecule, what you have probably been taught as a reflection of some abstract notion, maybe called the second law of thermodynamics, that gives time direction, is at play. We are going to try to understand the origin of such behavior from microscopics, from models as simple as this, just a random walk, a molecule equally likely to go up or down, left or right, how that can give rise to emergent macroscopic behavior like apparent irreversibility, which we've just shown is truly only apparent if we followed it long enough in time, or if we were able to watch an individual molecule, we would actually see things reverse themselves. Okay, so let's talk a few practicalities. So one of the most important practicalities is where these lectures and all their corresponding coursework will be posted. That will be in B courses. That's the website we use here at Cal to organize our courses. Let me log in here. Two-factor authentication is your friend. That's an important thing. All right, we are in fall 2020. So I want to pull up the syllabus to alert you to some facts. So as you all are aware of, if you're watching this, the lectures will be recorded asynchronously. I'll tend to try to post them Tuesday and Thursdays, or post them Mondays and Wednesday evenings so that you can watch them on Tuesdays and Thursdays. And what I hope to have happen is that you watch them ahead of time so that at 3 o'clock on Tuesdays and Thursdays, we can have a focused discussion for questions that arise as you watch the lectures. So that will be through the Zoom link presented here. In addition to those focused discussion times, I will have office hours also through Zoom at the link here. Tentatively, I've scheduled those for Monday from 3 to 4 and Thursday from 3:30 to 4. So a continuation of the kind of live focused discussion session on Thursday. Those office hours are subject to some change over the next week while we kind of sort out our schedules. It would be very useful for me. Maybe we'll do this in the live part of the lecture tomorrow. So during the first live session on Thursday, we can take a poll as to whether or not these sorts of office hours will work. So I've introduced myself. Another important person to introduce yourself to is Daniel. Daniel will be your GSI, your TA in the parlance of other universities. He will be in a very important resource for the class. He'll hold office hours as well as a weekly discussion section, which will be in part primers on some of the mathematics or physical concepts that we'll cover in the course that I will expect you to know, but will be useful to have refreshers on, as well as reserving some of that discussion section time for question and answers on the homework. You can go through the syllabus and read the sorts of topics that we'll cover in the class. You know, it's, as I said, at the top of the course, or the top of the lecture, this course is really meant to start the framework for statistical mechanics. I won't assume that any of you have had a StatMech class before, though I suspect some of you have. The lectures really are meant to be self-contained, so we don't have an official book. I won't assign problem sets out of a book, but should you want to follow along in a textbook, what I would suggest using is the Introduction to Modern Statistical Mechanics by David Chandler. There are lots of other reasonable books that you could also read up on. They're listed here. Many of these are available virtually through the library, so you can look at them online. I'm particularly a fan of the Chandler book for the following reason. So let's see here. So some of you, you're probably pretty young. I don't know who your Spider-Man is, but mine back in the day was Tobey Maguire, shown here. So in the first few Spider-Man movies, this was my Spider-Man. I'm a big fan of comic books and superhero movies. I want to be like Spider-Man. Not only, Spider-Man is particularly one of my favorites because not only is he a superhero, saves the world, but he's actually a pretty clever guy. He's a scientist. This is a snapshot of the first Spider-Man movie where he is also clearly a doting grandson. Now, if you're looking carefully, you might notice over here in the corner a stack of textbooks. One of them, very not so excitingly, says physics. This little green book here, if you were to zoom in, is indeed an Introduction to Modern Statistical Mechanics by David Chandler. So, I like to think that if you learn StatMech, maybe you too can be Spider-Man. So with some great StatMech power will come some great responsibility. All right, so that's the book. Again, it's meant to be self-contained, so it's not so important that you have one. Should you want to use it, that's the one I would suggest. Okay, so those are some practicalities. Let's go ahead and go back to the lecture. So, as I said, our goal is really to build an understanding of thermodynamics from basic principles, basic molecular principles. And we're going to start with something that you all should feel comfortable with. And it's what we've already reviewed. That matter, be it the liquid in my glass, the table I'm sitting at, or the tablet I'm drawing on, all matter is made out of molecules. And those atoms are in constant motion. Now that motion is chaotic and complicated. And should we want to say something specific, we would face a very difficult task. Saying exactly the trajectory a tagged water molecule traces out in time is hard. What we want to do is to say something about the system in aggregate, about the collection of water molecules, for example. And our starting point is to make an assertion, to assert a real bedrock principle from which everything else will follow. We will assert that in an isolated system, all microstates are equally probable. To which you should say, what? So let's define those terms. What is an isolated system? An isolated system is one in which there is no exchange of energy. Which we will often give the symbol E for. No exchange of mass or particle number, and no change in volume. So N, the number of molecules, V, the volume, and E are fixed. You can envision, should you wish, a box that is rigid, so the volume doesn't change, that I wrap in insulation, so the energy is constant, and that is impermeable, so the number of molecules trapped in that box does not change. So in such a system, a somewhat artificial construct, to be fair, but in an isolated system, all microstates, so what do we mean by a microstate? A microstate are all of the possible molecular details I can hope to specify. We'll give microstate the symbol nu. So what do I mean by all possible molecular details? That might be all of the positions and associated momentum of all of the particles. A ton of information. That would be Avogadro's number times 6, 3 positions, x, y, and z, 3 momentum for a classical system, which I am allowed to give both the position and momentum for. If I confront the fact that maybe the world really is quantum mechanical, it is, spoiler alert. What I mean by all possible molecular details is the full wave function of the system. Okay, so in a system which has its volume, energy, and number of particles fixed, every possible molecular configuration, every possible microstate is equally probable. What do I mean by equally probable? It means that the natural dynamics generate a distribution that is statistical and independent of its initial condition, but dependent on global constraints. Global constraints of having the energy, volume, and number of particles fixed. So this assertion that all microstates are equally probable in a isolated system is known as the ergodic hypothesis. It is the fundamental postulate from which thermodynamics and statistical mechanics follows. So we are resting our hat on this hypothesis, this assertion. We should certainly ask, are we sure? Does this really work? And if so, why should we expect this to be true? In fact, it should seem really surprising. So consider, for example, our dilute solution again. So if we were to peer into our little glass, your little dye molecules, this is one microstate where I have located the positions of some number of dye molecules. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. That's one microstate. Another microstate of 9 dye molecules, 1, 2, 3, 4, 5, 6, 7, 8, 9. That might be microstate number 2. This assumption says that the probability of seeing microstate 1 is equal to the probability of microstate 2. Now, my intuition, I don't think, would have expected that. One of those microstates looks a lot more probable than the other. In fact, I suspect your intuition says that one of those microstates is more likely than the other. And yet, let's think of another example. So a dilute solution, the arrangements of ink in our water is maybe complicated. Let's think about something simpler. How about some other random event? How about flipping coins? So that while the location of some dye molecule has some probability that we're asserting is simple, we know a lot about the probability of flipping coins. All right, so let's imagine I flip, say, 7 coins, and I get one, 2, 3, 4, 5, 6. A heads, tails, heads, tails, heads, heads, heads. That is a sequence of coin flips that I could assign a microstate to. I flip 7 coins. That is its configuration. All I could possibly tell you about the outcome of those coin flips is whether it's a head or a tail. Let's think about another microstate of a set of coins that are all heads. 1, 2, 3, 4, 5, 6, 7. That's microstate number 2. Now you tell me, what is the probability of seeing the specific sequence of coin flips on the left compared to that on the right? So what's the probability of flipping a coin and getting a head? That's 50%. If I flip another coin, what's the probability of getting a head? It's still 50%. So in fact, it is indeed the case that this specific sequence and this specific sequence, the one on the left and the one on the right, are indeed exactly equally likely. The probability that I get the specific sequence, heads, tails, heads, tails, heads, 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 is exactly equal to heads, 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 heads. It's 1/2 to the 7. And yet your intuition, I suspect, would have told you that the microstate on the right is much less probable. Why is that? Why do you think that that's less probable? Why does your gut tell you that it should be a pretty rare event to have seen 7 heads flipped? compared to seeing that specific sequence of head, tail, head, tail, head, head, head being flipped. What's going on? The secret is in the details. There are typically many more ways to appear disordered, to appear random. I'll use the term disordered states to be like microstate number 1 over there on the left of our coins, a seemingly random sequence of heads or tails. Then ordered states the sequence of all heads on the right. That should be contrasted with the microstate of our dilute solution on the left, which is seemingly at random. Had I drawn a different random distribution of solutes, you wouldn't have really probably known the difference. You would have noticed the difference compared to that nice regular arrangement over on the right. That seems like it should have been less likely for me to have drawn. I had to concentrate more on drawing it because I instinctively associate that regularity with difficulty or with lower probability. And yet that specific sequence, if we believe our postulate, is just as likely as that specific configuration on the left. And a heuristic way of understanding that is by thinking about coins, which natively or naively you might have expected obey similar sorts of rules. Probability of seeing all heads seems like it should be different than seeing some specific arrangements of heads and tails, and yet that is only true in aggregate. While there are many more ways to have written down a sequence of heads and tails that have the same number of heads and tails, there's only one way that I could have written out a sequence of 5 heads or 7 heads. So that's a heuristic argument. So why then should that assertion be true? Well, that's hard to say. I could throw my hands up and say chaos, the dynamics over which an Avogadro's number of molecules propagate is complicated. And so in our naivete, in our ignorance, the simplest thing that we could say is maybe each state, given some global constraints, are equally likely. So this is something which is hard to prove to be true. In fact, systems by which we can explicitly calculate the probability of individual microstates a priori are simple enough that this doesn't hold for. And yet all systems in which obey a thermodynamic description, which is, as Einstein would say, the one set of rules that will never be broken, actually do obey this postulate. So indeed, we take this assertion then as the fundamental postulate, the unprovable statement from which we can derive everything else. A mathematical representation of this postulate at fixed number of molecules, volume, and energy, the probability of any microstate is proportional to a constant. That constant we can write in this specific way. Oh, that's a very terrible omega. Let me try again. That constant then is just the number of microstates, and this is a constant if the energy of this specific microstate is the energy I fixed, the volume is the volume, and the number is the number. It's 0 else, and this omega then just counts up the total number of microstates that are allowed. So in an isolated system, if all states are equally likely, the probability of a microstate just depends on how many there are. So StatMech, in a very strict sense, something we will really come to appreciate over this class, is all about counting. Okay, let's go back to that beaker. Our glass of water. And let's now actually do a calculation to see how this postulate plays out and helps us understand this phenomenon of diffusion. Let's draw our glass, fill it with water, and now let's try to do a specific calculation. Let's imagine that this glass has an area, A, a length, accessible to some solutes that is determined by the location of some semi-permeable plug. So in the top of this beaker, I have N solutes in a dilute solution. I have a semi-permeable plug. Such that water can pass through the plug, but the solutes cannot. And the location of that plug, and therefore the volume accessible to the solutes, is then the length of that plug from the top, L, times A. And now let's ask a specific question. If that plug is free to move up and down, so how could it possibly be free? You're thinking, oh, that semi-permeable plug weighs something. Well, let's imagine that its density is the exact same density as the solution. So it's essentially density matched or massless for all intents and purposes. If those conditions are true, if it can move freely, where does it go? We are already in a position to answer that question from first principles given our postulate. So how can we sort that out? So we can note that each position of the plug, at each position, there are a number of microstates consistent with that position of the plug. So for example, if L was some L1, which happened to be right here, one possible microstate might look like this. Call that microstate 1. If I was going to look at another microstate, plug in the same place, I could arrange those N solutes in a slightly different way. That's another microstate. Call that microstate 2, and so on and so forth. or many microstates, many arrangements of the solute particles consistent with that plug being at L1. Similarly, if L was at some L2 greater than L1, say near the bottom of the beaker, I still have N solutes. There's a number of microstates consistent with that position. Plug in the same place. Different arrangement of the solutes, etc. Call this one microstate 2. So there's a number of microstates, each consistent with a fixed volume. If I fix L, the area of the beaker is not changed. That means the volume is fixed. For N being fixed, the number of solutes is not changing. The solutes are dilute, so they don't interact. So for all intents and purposes, we can imagine that the energy is being held constant. The probability that we find that plug at a given L should then just be proportional to the number of ways that I could have, the number of microstates that I can have consistent with that given L. So because each state is equally likely from our fundamental postulate, the probability we find the plug at L is just proportional to the number of ways that I can have that specific state of the system, that L state of the system. So if I was going to assign the probability of observing any one of those individual microstates, mu1 or 2, all of them at fixed L have the same likelihood. So the aggregate probability of seeing the system at L1 is just then the total probability of each individual microstate, which if they're all the same is then just proportional to the number of those states that are consistent with that L, and so on and so forth for different L's. So that means that the most probable L the most likely state of the system, the most likely position of our plug, is the one that maximizes the number of solute microstates. If the probability of finding the plug at L is proportional to the number of solute microstates at that fixed L, then the most probable position is just the one that has the largest number of those microstates. So let's do what we do in statistical mechanics and let's just count. So we're going to make our lives easy by introducing a scale to count space and states up into. So the plug is at L, the area of that beaker is A. Let's say that there's a maximum L max. Here are my solutes. Let's zoom in. And in order to count the number of solute microstates, let's grid up space. Let's introduce a scale. So each individual lattice site has a volume V. There will be sites that have no solute. There will be sites that have a solute. Let's let M be the number of cells, which, if they each have a volume little v, is just the total volume A times L divided by little v, not to be confused with nu. The number of ways that I can arrange one solute in those M cells, so how many boxes can I put one solute in if I have M boxes? Well, that's M different ways. If I have N particles to put in those M boxes, well, if the solution is dilute, I can put the first one in M boxes to a good approximation. I can also put the second in M boxes. So that's M to the N. And I've overcounted by a factor of N factorial because this configuration, for example, if I re-highlight that configuration, is insensitive, or it looks the same if I put the particle down in the bottom left down first, and then the particle at the right second, or if I did it vice versa. So there's a permutation accounting for the fact that particles are indistinguishable. Importantly, though, the number of those ways that I could put solutes down in M cells is proportional to L to the N. So the number of ways increases incredibly rapidly with L. So it will be maximized, well, where L takes its largest value. The largest number of microstates for distributing those in solutes occurs when I push that plug all the way to the bottom of the beaker. Now, if that plug is equally likely to, or is massless, so it doesn't take any energy, essentially it's acting as a fictitious divider, a way of thinking about different arrangements of the solutes just naturally. So what we've actually just uncovered is that, consistent with our physical reality, consistent with our everyday experience, is that solutes will spontaneously fill the container. Now, this might be the time where you start thinking, well, what in tarnation does this have to do with entropy? I was taught that entropy is why ink diffuses into a glass, and yet we didn't invoke anything to do with entropy. We didn't invoke a second law. We stated a fundamental postulate that in a closed system, all states are equally likely. And this is what emerged, a directionality that says that the solutes will fill the container. more on that next lecture. For the time being, let's ask, what if we could push back? What do I mean by that? What if we take this beaker filled with our insolutes and our plug, and instead of letting that plug move freely, we attach a spring to it. Let's now say that the distance from the bottom is Ls, that's the extension of the spring. And let's say that that spring, it's a mechanical object, it has some energy associated with it. Let's call that energy ES, and like most springs, will depend on its extension. So now L max, the maximum extent or displacement of the plug from the top, is given by L plus LS, its position where it is in this diagram there, plus the extension of the spring. And now those solutes, while they still do not interact, that spring, as it displaces, changes its energy. So there was some initial energy of the solution, call it E, whose total energy is now given by the sum of the solution energy plus the energy of the spring. And now moving the plug repartitions not only space, but energy. If I change L, that corresponds to a differential change in Ls. If I increase the distance of the plug from the top of the beaker, that necessarily corresponds with a decrease of the extension of the spring. Similarly, if I change the energy of the system, that comes about through a change in the energy of the spring. Change the energy of the solution, I must change the energy of the spring. So I can define a force on the spring in a way that I would normally define a force. F is the gradient of the energy of the spring with its displacement, which is now equal to how the energy of the solution changes with the displacement of the plug. All right, so now let's go back to counting. How many microstates do we have? Well, now the number of microstates, we need to keep track of both the length, or as a proxy for the volume, and the energy. And now let's make an assumption that that can be factorized into a set of microstates that are spatial microstates that depend on where the plug is, and a number of microstates associated with different energies. Now this turns out to be a good approximation, or it turns out to be exactly true, that you can separate those numbers if and only if there are no interactions between the solutes. Another point we'll discuss in much more detail later on, but this will suffice to help us get to a nice result. So if we make that separation, again, the most probable position of the plug maximizes the total number of microstates. Now, it will behoove us to not try to maximize omega, the total number, directly, but a monotonic function of omega, log omega, which is convenient, gives us the same answer. So finding the most likely value of the position of the plug can be done by maximizing the number of microstates, or the log of the number of microstates with respect to L, which given our factorization is d log the number of microstates associated with different partitionings in space and how it changes with L. It behooves us to use a log because then these derivatives are nice and simple. I have a product of terms. When I take the log, I get a sum, which when I then take the derivative, gives a sum of derivatives. So I'll write this change in L as a change in the number of microstates with respect to E, and then a change of variables of how E changes with L. If I want to find the most likely value, I want to set that derivative to 0. Now, one of these terms we've already seen. We saw that the number of microstates as I repartition space goes like L to the n. If I take the derivative with respect to L, I get n over L. Derivative of log L with respect to L is 1 over L. Log of L to the n can be written as n times log of L. dE dL, well, that's exactly what we called the force. D log omega of E dE, now that's some number we haven't seen before. Let's just define it as some variable beta. So if we put this together, we have n over L is equal to beta times F. That's the condition for maximizing the log of overall omega, the number of states consistent with a given energy and length. Let's rewrite this. If I multiply both sides by 1 over A, I have n over A times L. A times L is the volume. That's just the density. Beta times F over A. F over A, that's a force per area. That's a pressure. Let's call that pressure pi. So what have we just found? Rho is equal to beta pi. Now think about that. Have you ever seen an expression like that before? The density is proportional to the pressure with some constant proportionality beta. This is indeed a law that some of you might have stumbled across before. It's called the osmotic pressure of an ideal solution. That's neat enough. We'll give it a box. Whoa. Now, I haven't said anything about the fact that there's a solute or a solvent. I've said that that's implicit. So all of this actually holds if there's no solvent at all. If I had no solvent, essentially what I'm thinking about is a collection of solute molecules that are moving around in space, not interacting. If they don't move through a solvent, that's the same as an ideal gas. And that osmotic pressure would go to a regular pressure. So what have I just found? Another way to write what I've just discovered is rho times V. Well, rho is N over beta. I could write N not in terms of number of molecules, but in terms of number of moles. oops, sorry, that's not rho. PV, so I bring the volume over to that side. So I have a PV equals N over beta. Let's try that again. So associating pi with pressure, I could write this as PV is N over beta. If that N is the number of molecules, that's a big number typically. I could introduce Na as Avogadro's number, and then write N in terms of the number of moles, not the number of atoms. And if Na times beta, well, if that's RT, what have I just found? That PV is equal to, let's say N over Na is a little n number of moles. Na over times beta, that's RT, nRT. And PV equals, hey, PV equals nRT. That's a result you know. We've just stumbled across the ideal gas law, again, just from a simple postulate that says, in an isolated system, all microstates are equally likely. We've just uncovered the ideal gas law. We've just derived the ideal gas law from that simple postulate. In fact, if we let Kb be R over Na, the R, the ideal gas constant, over Na, Avogadro's number, that's a number that has a value in a specific unit system, which is really small, joules per Kelvin, for example. We'll call that Boltzmann's constant. And what we've just needed to invoke is that this beta is how the number of microstates change with energy, which if I associate Kb, Boltzmann's constant, with R over Na, what we'll discuss at length is that beta is 1 over Kbt. So this beta, how the number of microstates change with energy, is somehow related to temperature. So this is, at this point, taken as a definition. Our charge in the next lecture is to see if it makes sense. So we'll discuss that next lecture. Before we go, we need to look back at our ink. All right, let's look back at our ink drop here. So where is that glass of water? So I don't know about yours, but mine is very well mixed. No, just kidding. This is the one we did last time. Still sitting there at the bottom. What's going on? Turns out diffusion's really, really slow. So I'll see you next lecture.